So I'll first introduce myself. My name is Or Zook. I'm a faculty member at the Hebrew University. I'm at the Department of Statistics and Data Science. It used to be Statistics Department. Recently, it was renamed to Data Science, like other departments. And we have lots of data science activities, although this talk in particular will be more like classical statistics. And I was like Zar said, doing some work a few years ago in population genetics, or statistical genetics, comparative genomics, and things like that. The last couple of years during COVID, I was more like hiding somewhere in quarantine and doing some math. So this the last few papers, and so this talk will be along these lines. It's a tutorial, so I'll start with very basic things, and hopefully I'll get to more advanced things in my research, which is also related to that. We'll see if we'll have time. So, all right. So what I'm going to talk about is a very fundamental question in statistics, or probability even, is what do we mean by saying the two variables are dependent, and how are we going to detect that from data, right? So it sounds like a very, very basic question. So we'll start with the simple things, simplest scenarios, but then we'll add some complexity. We're going to ask what type of dependency do we care about? Do we have power to detect them? Is it identifiable from samples? What's happening when we don't just sample from the joint distribution of the two variables, but we have some biases? How are we going to correct for that? So things will get more and more complex as we go. And feel free to stop me for any questions. Right. Any questions? All right. All right. So, yeah, now I'll warn you. So I try to write formally the equation for most of the stuff I'm talking about, but I'll try to sort of, when I explain things verbally, I'll try to give you the intuition. So don't worry if you don't get all the details in the equations. So we have a very fundamental problem. So we have two variables, x and y. And we have an hypothesis testing problem. H0 is that they're independent, and H1, the alternative, is that they are dependent. And we have a sample of xi, yi, and n samples. That's our data. And we want to formulate a statistical test. So how are we going to do that? We have a test statistic, t, which is a function of our sample. And so we have a test statistic, but then we convert this test statistics to a binary variable, either 0 or 1, that signifies whether I'm going to reject the null hypothesis if t is 1, and accept the null hypothesis if t is 0. And we have the usual things in statistics. So alpha is our type 1 error. 1 minus beta is our power. And all right, so that's like the first thing. So that's how you formulate hypothesis testing in a general case, but specifically here for independence. Now notice that here, both H0 and H1 are composite hypotheses, right? They don't specify a particular distribution. Even if I tell you that x and y are independent, I didn't tell you what is the marginal distribution of each one of them. And H1 is any joint distribution that is not independent. All right, so just a nice cartoon that shows you, the trade-off between the two types of errors. So we have a test statistics that we compute from the sample, and under H0, the distribution is a blue distribution. I mean, that's not real data or simulation, it's just a sketch. Under H1, it's a red distribution, and we have some threshold here, and we're going to reject the null hypothesis if our test statistic is larger than this threshold. And right now, what is our error? So the red area here, that's our type 1 error, right? Because it's a probability under the null, under the blue curve that we're going to reject. So we want to make that small. And the sum, in that case, of the green and the red areas, so it's the area under the red curve, is our power. So we want to make this large, right? So because that's the distribution of our statistics under the alternative. And of course, we have a trade-off. If we move the threshold to the left, then our power increases, but also our type 1 error increases. So to get a good test, we want both alpha to be low and beta to be low. We want these two distributions, the red and the blue, to be very, as different as possible, right? So to be separate. All right. Here are some types of dependencies we have from, it's actually from Wikipedia. And we have one proposal for such a statistic, which is a Pearson correlation. So I think Saron talked about it a couple days ago. And so we have here simulated data of different types. And now on the first row, we see dependent data, but you see different strengths of dependence, right? So you have as you move towards the middle, you have more and more noise. So just an exercise, so to see that you're with me. On the first row, which distribution or sample looks like it's independent? Most of them are dependent, just one is independent. The middle, right, because we have a correlation of 0. All right. And now let's skip that, but in the bottom row, there's also an independent one. Which one? Anybody? Also, most of them are dependent, but there's one independent. The right? I have a different orientation for you. Yeah, you're right, this one. Right, so here, you might get confused because you have these different clusters, but really what you can see is that the joint distribution is a product of the marginals. So both marginals are bimodal distributions, right? So you have these two humps, but you don't really see any dependence. And all the other distributions are dependent. And this figure also illustrates a problem. So even though we have here very strong dependency, in some of them, the Pearson correlation is 0. Because it measures only linear dependence and not general dependence. Is that clear? Good, okay. Let's move on. So we're going to use other measures of dependence. There are many of them, but I'm going to survey a few of them. So some of them you might have heard, like things like Spearman correlation, Kendall tau. These are non-parametric versions similar to Pearson, but they can only detect monotone dependence. And we are going to actually focus on more general things. So three particular ones are Decor, Meek, and Chatterjee coefficient. And there's actually another one, Hofting's statistic, which I'll mention in a bit. And these ones are meant to capture any kind of dependency. And as you can see, even though it's a fundamental problem in statistics, you might have thought that people have figured it out like 50 or 100 years ago. There's still lots of research activity, even in the recent years, about this problem. And we're going to focus on continuous variables. For discrete variables, there are more natural, I would say, measures of dependence. For example, you can take the mutual information. And this, for information theory, we know that the mutual information is 0 if and only if the variables are independent, right? So you can, so we have a measure, a good measure. You can also take another measure. For example, we can do a chi-square test. So we have the observed versus expected in each pair of xi and yi, and this will also serve us for a good test. So that's for discrete. There are still problems with discrete, especially if the number of categories is large, then these things might not work well in practice and you need to do more clever things. But we're going to focus on the continuous case. All right, and just to motivate you, here are some examples. That's from the papers that introduced one of these coefficients called Meek by Reshev et al. And these particular data sets are from metagenomics. And we have here the abundance of two microbial species in different samples. And they vary based on either nutrition or some other interventions. And what you see here is a very interesting pattern of, it's called mutual exclusion, right? So clearly, if you look at this data and you look at the points, then there is a dependence between this bacteria species and this one, but it's non-linear. So basically what you have is you can have very little of both. So you can have a lot of one of them or a lot of the other one, but you cannot have anything here. Right? So it seems the niche is good only for one of these bacteria. And if you just use linear methods, they might still detect it because you can do a regression or Pearson correlation here. It will find it, but it will have less power because the true shape of the distribution is highly nonlinear. Right? That's just one example to motivate you. Here's another one from a very recent paper, actually a year ago, and that's called U-shaped distributions. So one particular type of nonlinear dependence is U-shaped, and that's very common in biology and not only in biology. Why? Because for many things, it's not good to have too much and not good to have too little, right? So this one is for temperature. So if we'll be here at like 60 degrees Celsius, we will not be very happy. And if we'll be at minus 60, we will also not be very happy. But in the middle, at some point, we are well off, right? So if you measure anything interesting here that represent desirable biological traits, you expect to see at the extremes of temperature, for example, that these things will be low, and then in the middle you have some certain maximum, right? And that's true for temperature, but it could be true for many, many things, like the number of calories you consume per day, or the level of some hormones, right? So all these things, too little or too much is not very good. All right. So that's it for the talk in terms of biology. So for now, it will be just statistics, just to motivate you. So now let's see a few tests, and it will show the challenge of dealing with continuous data. And what we are really trying to do, at least in some of the tests, is sort of reduce the problem to the problem of discrete data. So I told you, so for discrete data, we know what to do. So if we have a few cells, we just look at the counts. How many observations did we see in the cell versus how many do we expect? If we have continuous data, then we don't have cells, so we can do things like, actually, it's very good that I'm projecting on this screen. So you see that we can use a grid, right? So we have this grid, so we have these cells, and we can count on each cell how many points do we see. That's our observed, right? And what will be our expected for testing independence? Anybody? Exactly, the product of the marginals, right? So, for example, if I look at this cell and I see one count, then my expectation will be all the counts in this row times all the counts in this column, right? And normalize appropriately, right? Because that's what happens when these things are independent. But, okay, so this in principle work, but when you have continuous data, there is a question of how do you divide into squares or rectangles, right? What is the grid size? How do you vary it when the sample size increases and increases? So, right. So what so there are methods that do that actually use a grid, and you need to specify very specific rates at which you decrease your or increase your resolution or decrease your cell size with n, with the sample size. I want to present a slightly different method, actually a classic one by Hoffning, that is doing something a bit different. It's really looking at grid of only only one line, one horizontal and one vertical line. So we have only like a 2x2 table, but it will do it many times, right? So the idea of Hoffning test statistic, it's actually, you can call it a classic paper. It's from 1948. We look at a grid of 4 different regions, and how do we determine the boundaries of the grid? We just take one of the data points. So here we have a data point. So we pass a vertical line here, a horizontal line here, and then we count here the number of observed points and versus the number of expected, which will be the product of these two times these two. And we get a 2x2 table, we get a statistic. Now, the problem with such grids is that they might not detect any dependency, right? For example, it could be that by chance, the number of points in each of these four rectangles agrees with independence. But within the rectangle, we might see like crazy things, like maybe here we have some shape of dependency between x and y. So one such partitioning to four regions is not enough. What the statistic is doing many such partitioning. And basically, we are going over all the data points. And for each data point, we partition again. We create another 2x2 table. And then we have n test statistics, and n 2x2 tables and n test statistics. And our Hofding test statistic is summing all of them. Right? So we have many 2x2 tables, and our statistic is summing all over all of them. Is that clear? All right. And you can prove that this works. What do I mean works? I mean when the sample size increases, this statistic converges. Well, anything that converges in probability theory, you have to say converging probability or almost surely or something like that. But it converges to this population version, right? So that's also very common in statistics. So you have some property of a distribution, and you approximate it based on the sample distribution. So for example, if our property is the expectation of f, then we want to approximate it by the mean, right? Yeah.
Well, does that anyhow relate to the Hofding bound on probability? Because then you have some assumption on the input.
Okay, you mean the Hofding inequality?
Yeah.
Oh, yeah. It's a good question. I don't know if it's related, other than being the same person. It could be that maybe in the convergence result, maybe the inequality is used. I don't know. Good point. So just like we approximate the expectation by the sample average, we can approximate this quantity here, this integral, by this statistic. And if you look at this integral, it actually tells you something about dependence. It's some distance between the product of the marginals and the joint, right? And clearly, this is 0 if they are independent. If they're independent, then for any xy, fxy will be equal to fx times fy. And then the integral will be 0. And for any dependency, and linear or nonlinear, doesn't matter, we have some region with measure more than 0, so positive probability, such that this will be different from that. And then when you do the integral, this will be some positive constant. Right? So that means that this Tn, converges to 0 if they are independent, and converges to something larger than 0 if they are dependent. Right? And using that fact, you can prove what's called consistency. Right? So I will not go too much into the details. What do we mean by consistency is that when n goes to infinity, things work, which means it means that our error goes to 0. If it's really independent, then our test will accept the null hypothesis. And if they are dependent, then our test will reject the null hypothesis. All right. Yeah.
Is this invariant to sign? It's not obviously, like if I do x and y or minus x and y, do I get the same answer?
Yes, this particular statistic, yes, because
the one that it converges to, I don't see the sign independence. Maybe it is, I don't know.
I think it is.
Okay.
I don't know.
Because it's looking at cumulative distributions, and when
Yes.
you accumulate the other way, it's not obvious.
Yeah, you're right. It's not obvious. Yeah, just a good point for those who might not have noticed. This is the cumulatives, right? So in many distances between distributions, we look at some integrals of the densities, but this is actually integral of the cumulative. Right. So, okay. Nice exercise, I guess, to prove that this is invariant to sign. And I'll talk a little bit more later, more generally about invariance, like what kind of transformations do we want our variables to pass through such that the measure of dependence will not change. Okay. I want to show another one, just as an example, a more recent one. It's called DCOV. So previously we had a very classic one. This one, DCOV was published in 2009 and made a very large impact, at least in the statistics community, but I think also elsewhere. And it's also a very nice idea. Basically, we know that Pearson correlation is good for linear things. So how are we going to use it for detecting any nonlinear dependence? So the idea was not to correlate x and y, but to correlate the pairwise distances. So for each pair of observations, I and j, we calculate xi minus xj and yi minus yj, because aij and bij. Now you get not a vector, but you get a matrix, right? Because you have all the pairwise distances. So we have two matrices, A and B. And we want to sort of correlate the matrices. We have to normalize. So here we have, so when you normalize the matrix, it's a little bit more tricky than a vector. You reduce the mean of the row and the mean of the column, but then you have to compensate, so you add the overall mean. And then you just take the dot product. That's your what they call DCOV, distance covariance. If you want a correlation measure, you also normalize by the standard deviation, and that's called DCOR. It's distance correlation. All right, so very neat idea, a pretty simple trick, but has very many desirable properties. And just to illustrate this idea, I'll show you a simulation. So on the left, we have the data. So what I've done here is just simulate a bivariate Gaussians with positive correlation. So if you just have positive correlation, you can use Pearson. But I flipped the sign of one of the variables randomly. Right? So maybe you can see here that there is really an X shape. So you have things here, and you have things here. Before I flipped the sign, everything was here. But now when you flip the sign, you also have things like that. And there's clearly, I mean, the sample size is low, but there's clearly a dependence here. But because I flipped the signs, really the Pearson correlation is non-significant. Right? But now when you take all the pairwise distances and you plot them against each other, you see a strong correlation between. So this just illustrates how DCOV manages to detect this dependence. Any questions? Yeah.
Just do Euclidean distance here and between points?
Yeah.
And would it work if you were to use other forms of distance? Like, does it have to be Euclidean distance?
I don't know. That's a good question. I mean, there are also consistency proofs for this particular one. I don't know what happens when you use other metrics. Another point I did not say is that this, of course, Euclidean distance you can also do for vectors. So I'm showing here everything for scalars, but you can actually apply this coefficient for vectors. So x and y can be vectors, and they don't have to be of the same dimension. So if you have, I don't know, embedding of things, into, now everybody likes to use this large language model or other models and embed things to vectors, right? So if you have embedding things to vectors, you can just look at the dependence between two vectors, right? Or it can be, I don't know, vectors can be two sets of genes or two chromosomes, etc. Because here you take the Euclidean norm, or the Euclidean distance between two vectors. Okay, good point. Other questions?
Yeah, the plot on the right, the red line, that's just a correlation again, or is there a way to visualize the DCOR?
Well, this is just, I just put here the regression line, yeah? Okay. But the DCOR is really, the normalization is a little bit different because the values are organized in a matrix. And of course, they are strongly dependent in each other, right? Because you take n data points and you generate from them n by n matrices, right? So it's not really like we are used to think about correlation, about independent observations. Yeah, but the statistic is still, you just take, after you normalize, you just take this, which is the correlation, if it's normalized. Right. And like Hofding statistic, also for DCOR, there is a population version. It's a little bit more complicated. It uses a characteristic function of the random variable. So I don't know how many remember from probability courses. It's a very fundamental function for random variable. But again, it has a desirable property that if the variables are independent, then this difference will be 0. And if they are dependent, it will be positive, the integral. And based on that, you can prove consistency, etc. also for this one. More questions? We'll move on. Okay, good. Now, you can ask, like someone was asking, like, what is it invariant to all kinds of transformations? So in recent years, I've seen there's been some activity in trying to say, what do we really want this dependency measure to satisfy, right? Because people were coming, everybody was coming with their own coefficient and their own tests. And in each paper you have some simulations that shows that this method is better and the other method is better, etc. And the question is, can we sort of build more an axiomatic approach? We first say, okay, what do we want our coefficients to satisfy before we decide what is the measure we care about? All right, so for example, in information theory, when you look at the entropy, you can sort of arrive to this function based on a few axioms, and then it will be the only function that satisfies them. Right. So these are some properties that people say that are desirable. For example, if we want the measure to be something like correlations, or correlation squared, like R squared, so we want it to be between 0 and 1. There is a question of, do we want it to capture the sign or not the sign? But when you have nonlinear dependency, it's not always clear what does the sign mean even. And you want it to be 0 if and only if they're dependent. So independent, I'm sorry. So any dependent pair, you want it to be positive. And for example, let's do exercise. Which of the measures I showed so far doesn't satisfy this one? Pearson correlation, yeah, exactly, right? Because you can have dependence, but still the correlation will be 0. So I think, Sharon, from now on you are forbidden to answer questions. I need some other participants, right? And we want it to be 1 if and only if there is full dependence. Now, full dependence, it's a little bit tricky to define. I mean, you can think of it as x being a function of y or y being a function of x. But sometimes it's not symmetric. So for example, if you have a line, I don't know, if you have 2 lines like that, right? So x is a certain number, and y can be either x or minus x, something like that. Is it really full dependence or not? It's not clear. Right? So some of these properties, I'm not defining them mathematically, accurately, just giving you sort of what we want in a little bit more vague sense. We want it to be symmetric, right, like Pearson. And we want it to be invariant to transformations. So for example, linear transformation. So we heard about the regression coefficient, which is not invariant to linear transformations. Right? In particular, when you multiply by a scalar, it changes your beta coefficient, but the correlation coefficient is invariant to this transformation. Right, so we want that. And if we care not just about linear relationships, but any relationships. So maybe we can require stronger properties. For example, not just linear transformation, but any monotone transformation, right? So if I, for example, here, take x and sort of stretch it in certain places, here and maybe here and maybe here, and squeeze it, so I change the marginal of x in different places. But I don't change the dependency between x and y. I might want the coefficient to be the same, right? And I know how many of you are familiar with that, but in economy, it's pretty popular to model separately the dependence between x and y, and separately the marginals, using what's called copulas. I don't know how many heard about that? Yes, right. Some, right? So if you do that, it makes sense that when you change just the marginal, the copula doesn't really change, and so the coefficient that measures the strength of dependence between x and y doesn't change. Right? So that's another desirable property. And there's also something called equitability, which basically says that if I have a certain amount of noise, then the coefficient will only depend on the noise level and not on the exact shape of the relationship between x and y. Okay, these are all very nice properties. There are a few more, but sadly, you cannot satisfy all of them. So there's also, like I said, there's some activity in this area theoretically. It's analog to, again, something for economics, which is called, maybe some of you know, of Arrow's theorem, right? So Arrow's theorem is talking about how to do elections, and you have more than 2 candidates, and every person is ranking their candidates, and you want to come with a population ranking, and you want this ranking to be to have certain properties, desirable, and what Arrow's shown is that you cannot do that, right? You have to, there's no ranking that will satisfy all properties, right? You got a Nobel Prize for that. So here's maybe your next one. So to prove that for different combinations of properties, you cannot have a coefficient that will satisfy all of them. So there's a nice discussion of some of these properties in a recent paper by Chatterjee. And he also proposed a new coefficient, which is that. So I'll just, it looks very simple. It is pretty simple. What you do is you take your pairs of samples, and you sort them based on x. So you have like the smallest x is here, but you also have the y that is paired with it. And then you have the next one, etc. And then you look at the ranks of the y's. Right? So if there is a strong dependence, then the smallest x will be together with the smallest y. Right? And then the second one will be the second one, and the largest x will be with the largest y. Right? If they're independent, you'll get something else. So there's this rank will behave differently, and that's a statistic. Now, another exercise. Which one of these properties does this measure not satisfy? That's a little bit harder. You can guess. Symmetry, exactly, right? So the way it's defined is not symmetric, but it's, it's not just a matter of definition. It really is non-symmetric, right? So if you define it the other way, so psi of y and x, you get a different coefficient. And some people argue that that's okay, right? Because somehow you want to capture how much dependency do you have when you try to predict y from x or x from y, and these are not always the same problems. Right? And there are other coefficients which are not symmetric. Probably many of you know also in information theory there is a non-symmetric function. It's called the relative entropy, or Kullback-Leibert entropy divergence between 2 distributions. It's not symmetric, but it still serves at some kind of distance between distribution, and it is useful for many, many applications. So it could be that sacrificing symmetry is not such a bad thing. All right. So there are many variations of this problem. Do we look at continuous, discrete things? What kind of dependency are we looking at? And sort of, I didn't make this distinction clear, but we really have here 2 problems. One is testing. Do we only care if they are dependent or not? Another one, if we actually want to measure, to say that these 2 are stronger than these 2, et cetera, et cetera. And these are the coefficients I show you so far. Another thing that's important is sampling. So far, we just assumed that we are sampling from the joint distribution fxy. Right? But in some cases, we have biased samples. And then the problem becomes even trickier. So that will be the second or maybe the last part of the talk. So yeah, we'll see how far we go depending on time. So what do I mean by bias sampling? So I'm writing here as a general, in a general form. Suppose that you don't sample from fxy, but you have some weight function, wxy, and you sample from this product, right? And it's proportional because when you multiply a density by some weight function, you need to normalize it. But this gives you a different density. And of course, we all know that biases can lead us to wrong conclusions. So when we get the data, we cannot just take our previous statistics and use them on the biased data. We have to somehow correct for W. Right? And biases, all kinds of biases are very common. Sometimes they are known, sometimes they are not known. For example, in medical data, I think many of you guys are doing, what's a very common bias that we have? A known bias. So when we do case control studies, right? So if we have a certain proportion of cases in the population, usually in the sample, I increase the proportion of cases, and then my sample does not have the same distribution as the population, right? So that's a simple kind of bias, but you can have many other and more complicated. So the question is, how can you, from this bias sample, detect whether or not X and Y were independent before you applied this bias? And it's a harder problem, so we're going to make it a little bit easier on us. We're going to assume that the bias is known. Otherwise, it's really, really hard, or sometimes it's impossible. So here's an example. Sometimes there's a bias that really tells you that you can only see points where Y is bigger than X. This is on the right. And maybe that's what's called left truncation, and there's also what's called double truncation. You can only see points within these stripes, right? So if I didn't tell you that there was this bias, and you just look at the data, you would of course say, of course, this is dependent, right? But it could be that you see this structure only because of the way you sampled. And within these regions, to me at least, these things, the X and Y don't look really dependent, right? If, for example, I would see maybe many points here in this stripe and nothing here, or maybe like that, then I could still conclude that there is dependence between X and Y, even though I sampled them via some bias mechanism. And there are, I won't don't have time to go into the motivation, but there are real life stories that lead you to this kind of bias. Sometimes you have patients that are in the hospital, and you can only measure them while they are there, and then they leave, so you don't see them, et cetera, et cetera. So what do you do? So there's a nice paper by Tsai doing what's called a permutation test. So just a quick check, how many of you know permutation tests for statistical significance? Okay, most of you know, good. So what we're doing is we have a test statistic, and then we permute the data. We take each xi and we couple it with a different yj, random one, and then we calculate the test statistic on this permuted data. We do it many times, and if the real data statistic is very far from the permuted data statistic, we say it's significant. Now here you cannot do that, because what happens is when you permute the data, let's say I have this point here and this point here, so it's this. So when I permute, I really get the other two, right? So it's two diagonals. It means that I will get a point here, right? So I cannot really do permutation test, because then my permuted data will violate this bias, this sampling. So there is a clever way to sample permutations, but only what's called legal permutations. So only ones where, even after the permutation, all the data is here, right? So it's a nice algorithm. And then you have your test statistic. You can sample on not all the n to the factorial permutation, but only the subset of permutations that agree with your bias sample or with your truncation. And you can get a p-value based on that. And that's a fundamentally different distribution from the distribution over all permutations. Right? And it was extended to double truncation. And what we did in a recent work with Yaniv Tenzer and Micha Mandel, they were both in my department. Micha is still there. We try to generalize it for any bias function, any W. So we don't have much time, so I will not go too much into the details. So first we need a new definition of what's called quasi-dependence. Why? Because it turns out that sometimes you cannot really tell if the X and Y are dependent or not based on your bias sample. So some dependents are destroyed by this mechanism of bias samples, but we still want to detect the ones that are not destroyed. Right, so if we're independent before, then we must be independent afterwards, but vice versa, it doesn't true. So this is just to show you an example. If your bias sample, here your distribution is only in this triangle. So X and Y are uniform in this triangle, which means that they are strongly dependent, right? Because you cannot have any points here. But if you sample points only here in the green area, then you cannot really tell, and that's the data you see. You cannot really tell if this came from a dependent distribution or an independent distribution, which will be this one, right? So if you have this uniform distribution over the unit square, after you use the bias sampling, you will get the same sample or the same sampling distribution as the one that was dependent. So again, so we have certain bias samplings that after we apply them, we cannot really distinguish between dependent and independent data. So we have to change a little bit the definition. And if we can detect it, we still need a test statistic and a procedure to apply a p-value. So that was the essence of the work we did in this paper. In the interest of time, I will just give like a couple of sentences of each of them. So in terms of the test statistic, remember we had this Hofding test statistic, which is here. So we're using the same test statistic, except that now the observed is the same, but the expected is different, because we observe not fxy, we observe fxy times this w. So you need to somehow correct for that. So we have a different, right, like we were saying, for the expected, you need to take the product of the marginals. And when you have this bias, estimating the marginals is not trivial. So we have a step of estimating the marginals. Then you get these expectations, and you can use this statistic. Okay, that's one. What is your statistic? The other part is how do you determine a p-value? And now it turns out, like here, like in this nice paper, that you have to sample permutations only that satisfy the truncation. We do it more generally. We sample permutations such that the probability will be proportional to this w, this sampling probability. And to do that, you cannot really sample directly permutations, but what we do is a Markov chain Monte Carlo algorithm. So you traverse the space of permutations in a certain particular way such that your stationary distribution will be indeed proportional to this bias sampling mechanism, right? So that was our paper, published recently. Here you see all the details of the MCMC. You'll have the presentation. And let me just wrap up. Of course, we have simulation results. And this is our method, weighted permutation. This is another variant of our method, which is using not permutation test, but the bootstrap. So the bootstrap gives you an approximate p-value. The weighted permutation gives you an exact p-value, but the bootstrap is simpler to implement. And we beat some other methods, in their own game, so for truncation. In addition, there are other scenarios that other methods cannot handle. So for general weight function, and these are some examples of real data. So here we have left truncation, double truncation. So and these are two biased sampling mechanism where W is strictly positive. One of them is just WXY, just a sum of X and Y. The other one is a bit more complicated. All right, so this is just examples for real data. And let me just conclude. We've seen many methods for detecting independence. Sorry? Okay, let me just wrap up. Many methods for either testing for independence or measure independence. There is a fair amount of theory for these things without bias. With bias, we have some work in progress that if you are interested, I'll be happy to talk to you about that. We need some improvement. Our method is slower than the general, the simpler method because we use the MCMC for permutations. And there are also interesting things about not just bias, but what's called censoring. Sometimes it's not that you don't see the point XY, but you actually see the point X and then the minimum of Y and a certain constant. And the question is, how do you correct for that, et cetera, et cetera. So with that, I'll just thank my collaborator, Yaniv Tenzer and Micha Mandel, and thank you for the opportunity to speak here.